Assuming that a is a given positive number, find the general solution to this differential equation. So dy by dx is equal to a plus 2, whatever a is, times x to the power a minus y over x. Okay, if we're going to find the general solution to a DE, differential equation, we probably need to find out what kind of differential equation it is, because you apply different techniques to different kinds of differential equations. So what have we got? Well, you got dy by dx, okay, first order, but we also have just this lone y by itself, part of this term. I mean, it's by itself in the sense that there aren't any other y's. Yes, I know it's being divided by x. So what we might do, this kind of fits the form of a linear differential equation. At least that's what jumps out to me right away. And if we rewrite this, dy by dx, or you could write y prime, and then we write plus y over x, although I'm going to write that as 1 over x times y. And just leave the a plus 2x to the a over here on the right-hand side. This looks like a linear differential equation. Okay, so this is nice and linear. And having recognized that, well, now we say, how do I solve a linear differential equation? And the first thing we need is an integrating factor based on this p of x, based on the function of x coefficient of our mystery y. Right? And the integrating factor looks like e to some antiderivative of our p of x. Okay, well, in this case, what's our p of x? 1 over x. Okay, so we need to raise e to the power of some antiderivative of 1 over x. For example, ln of x will do the trick. So let's say something like, here's our integrating factor. Okay, it's integrating factor e to the ln of x, except, wait a minute, e and ln, these are inverse functions. They cancel each other out, and you're just left with just x. So x would be a great integrating factor. What do we do once we have our integrating factor? We multiply both sides of our differential equation by this x, a plus 2x to the a. So we'll multiply x here, and multiply an x here. So that simplifies to x dy by dx. These cancel out. 1 times y, we'll just write y. And a plus 2, that's a constant. I don't know what a is, but a plus 2 is just some constant. X to the a times x to the 1 is x to the a plus 1. So there we go. We took our differential equation, we multiplied by the integrating factor. So why did we do this? Why did we find an integrating factor? Why do we multiply both sides by it? Well, take a look at our integrating factor, x, times y. If I took the derivative of that using implicit differentiation, you would get x, now just use the product rule. You get y times the derivative of x, which is just 1, but oh, this is the left-hand side of my expression. So this left-hand side here can be rewritten as integrating factor times y, the unknown function we're solving for, and then the derivative of that. Right? That's the whole reason behind this technique. The integrating factor allows us to rewrite the left-hand side as just an expansion with the product rule of a derivative. Okay? So we get that on the left-hand side. The a plus 2 x to the a plus 1 stays where it is on the right-hand side. And now we're trying to isolate for y. Okay? This has been, we've made some progress, so this has been progressive because, we don't have any more dy by dx. We don't have any more y primes. We just have a single y here. Okay? We take that y, multiply it by x, and then take the derivative. Okay? And so how do we work through algebra with just one unknown in our equation? We slowly undo our operations in reverse order. How do you cancel out differentiation? Integration. Okay? So if we integrate both sides, whatever you do to one side, you have to do to the other side. Otherwise, you're not allowed to keep the equal sign. Integration and differentiation, they cancel each other out. And so then you're left with x times y on the left. Right? We're slowly getting closer to that x. over here, oops, on the right-hand side, increase the degree by 1. So we've got this a plus 2, that's our constant here. Increase the degree by 1, so it goes from a power of a plus 1 to a power of a plus 2. Divide by the new degree. Oh, look at that, everything cancels out. And then plus c, because we want the general solution, right? That's what they're asking for, general solution. So there we go. X times y is x to the a plus 2 plus some arbitrary constant. And we just want y by itself, so we divide both sides by x now. Which we could rewrite as x to the a plus 1 plus c over x. Right? So it doesn't actually matter what a is. We were still able to solve this, and we got our general solution. And we can write it as c over x, or if you wanted to, you could say c x to the minus 1. That way it all fits on one line, no fractions. And there we go. That's our general solution. Regardless of what a was, it all worked out.